Akira Suzuki and Eiichi Negishi received the 2010 Nobel Prize in Chemistry. They developed techniques that are used to make LCDs, drugs, and many other common items. Their method, called cross-coupling, links up carbon atoms. Japan is a leader in this area of chemistry. What was the motto of Suzuki-san and Negishi-san's mentor? And how did they carry out reactions once thought impossible? Today we interview Akira Suzuki and retrace his journey to becoming a Nobel laureate. Hello.
Hello.
This is Science Zero. Today, an exciting story. 2 Japanese received the 2010 Nobel Prize in Chemistry, and we're featuring these 2 researchers.
When I heard the news, I was really happy. In 2008, there were also Nobel laureates named from Japan. It renews confidence that Japan is doing great scientific work.
I watched the announcement live on the internet, and I was thrilled when I heard their names read out.
Yes, it really was exciting. Let's take a look at the 2 scientists who were honored. Emeritus Professor Akira Suzuki of Hokkaido University and Distinguished Professor Eiichi Negishi of Purdue University in the US.
The 2 were selected for the Nobel Prize for their work on cross-coupling. Had you heard of cross-coupling?
No, it's a new term to me. But now in Japan, it's very much in the spotlight.
Now Suzuki-san recently came to Tokyo, and I was able to meet with him for an extensive interview. Hello. Thank you for making time in your busy schedule. This way, please. First of all, congratulations on the Nobel Prize.
Oh, thank you very much.
Have you ever watched our program?
Oh, yes, I have. I watch it every week.
You do? That's great to hear.
Well, sometimes I miss one, but I generally watch it.
Well, thank you very much. The coupling techniques that you developed are now used in making many products.
It's something shared by all researchers, working in all kinds of fields. The dream that their work will one day prove useful. So I am overjoyed that what we discovered went on to be of tremendous practical value. It makes me very happy.
Cross-coupling, the basis on which this Nobel Prize in Chemistry was awarded, is a technique with broad applications. It is used in making electronic products such as LCD panels. Without the work of Suzuki-san and his colleagues, today's TVs, mobile phones and digital cameras could not exist. This is a blood pressure lowering drug made using cross-coupling. Innovative drugs that protect our health are another application of cross-coupling. Cross-coupling is a type of reaction that links together organic molecules which otherwise would be difficult to combine. It is a kind of magic glue for molecules, a breakthrough technique that allows totally new organic compounds to be made to order. Suzuki-san published his key paper on cross-coupling in 1979. He was then an assistant professor at Hokkaido University. The paper was the fruit of 30 years of research. Suzuki-san was born and raised in the town of Mukawa in Hokkaido. Even as a boy, he was fascinated by mathematics and science.
All the other kids would be playing. He would be reading books by himself. I saw him reading books all the time. That's what I remember. Whenever he wasn't satisfied that he fully understood what was being taught, he'd raise his hand and ask the teacher.
He had a lot of books in his room. A lot of the ones he showed me were books that were related to our studies. Things like reference books. He would sometimes show me these kinds of books.
When you were a child, you liked science and mathematics.
Oh, yes, I did. I was the same back then as I am now. With mathematics, the answers are clear. 1 plus 2 is 3.
Only one right answer.
One right answer. But in fields such as, for example, the social sciences and humanities, 1 plus 2 doesn't necessarily equal 3. There are multiple possible answers. I prefer the clarity, the simplicity of maths and science. I like a straight answer. So that's what I like, although I couldn't have thought of it this way when I was just a boy. All I knew back then was that I liked maths. And thinking back on it later, in terms of my personality, I realized that I was wired to like simplicity. And that's why I enjoyed maths. At school, I could answer the teacher's questions correctly and fast, and I was praised for it, which made me happy. That may also have been a factor, but I'm not sure.
In 1949, Suzuki-san entered the Hokkaido University School of Science. But his life as a student didn't always go smoothly. His father had already died, and he had to leave school for a year to earn tuition money, working as a teacher at a middle school in his hometown. One of his fellow teachers at the school was Yukio Miyazaki. He vividly recalls what Suzuki-san was like at that time.
He got along so well with people, and he was liked by all the children. They called him by his first name.
In his second year at university, Suzuki-san came across a certain book. It was an organic chemistry textbook published in 1952. It was this book that set him off on the path of organic chemistry.
Let me ask you about your university years. In your second year, you came across a book.
Oh, is that the same book?
Yes, this is that book. The textbook of organic chemistry.
Ah, yes, Fiese's book. I think it says that it's the Asian edition. Louis Fiese was a Harvard professor. He wrote the textbook somewhere around the mid-1950s and published it as a textbook. That's how this book came about. The paper quality is poor. It would be unthinkable in a book today. But this book had a huge impact on me.
In what way?
Oh, in so many ways. For example, it describes analytical instruments. Organic compounds are composed of, say, carbon, hydrogen, and nitrogen, among other elements. The instruments described here are used to analyze the amount of carbon and hydrogen, and so on. There were almost no books like this written in Japan at the time. There were certainly none like this that you could read and then get right to doing experiments. Another thing is that this book covers systematic organic chemistry nomenclature. There are all kinds of organic compounds with prefixes like mono, di, tri. Now these are the easy ones. The difficult ones are the ones with additional modifying nouns. It's difficult to get them straight. For example, the chemicals known as dibasic acids had a mnemonic. Oh my, such good apple pie. The O is oxalic acid, the my is malonic acid, The such is succinic acid, the good is glutaric acid, and so on. This mnemonic that helps you remember the names is in Fiese's textbook somewhere. I thought that was interesting. And thanks to the mnemonic, oh my, such good apple pie, even now, 60 years later, I can still remember those dibasic acids. Oh my, such good apple pie was in the footnote somewhere, and I memorized it.
So this book sets you on the path of chemistry.
That's right.
There was another book that had great influence on Suzuki-san's career as a researcher. He came across it at the age of 32 when he was an assistant professor at Hokkaido University. The author of the book was Herbert Brown, a professor at Purdue University in the US. Brown would become Suzuki-san's mentor and later win the Nobel Prize for Chemistry in 1979. Brown's book presented his research on a boron compound. Boron compounds were crucial in Suzuki-san's later discovery of cross-coupling reactions. This book directed Suzuki-san along the path to his Nobel Prize.
Well, speaking of books, here is another one that I understand was pivotal in your career.
Oh, yes, very much so. Hydroboration by Herbert Brown.
Synthesis of organoboron compounds.
Yes. The process is generally referred to as hydroboration. It was discovered by Professor Brown. Synthesizing organoboron compounds had been very challenging. This made it quite easy. The book came out in 1962. I went to the bookstore and found this, and the reason that I noticed it is, well, see this red and black color? The binding looks more like a literature book. On the chemistry shelf, it really stood out.
It caught your eye.
Yes, I wondered, what's this book? And I saw the title. Professor Brown later told me he'd chosen the colors because of his wife.
His wife?
Yes, Mrs. Brown liked the colors, red and black. So the book was bound with this design because of her. Professor Brown told me that himself, so I'm sure it's true. So Professor Brown wrote hydroboration, but Mrs. Brown chose the two-tone color scheme. When I went to buy some chemistry books, there were quite a few to choose from. But because of the unusual binding color, I spotted this book. And that set me off.
So perhaps if it hadn't been for that two-tone binding...
Well, then maybe I wouldn't have seen it. Life is full of those little coincidences. I stayed up all night reading that book, only that one. It's not such a big book. How many pages is it?
Well, let's see, 283, not even 300 pages.
Short enough to read in one night.
But reading this book took you down the path to the Nobel Prize. Were you at a dead end in your research at that time?
Well, no, not at all. Back then I was interested in working on the Schmidt reaction. It seemed interesting. Then I happened to see Brown's book. I turned away from the Schmidt reaction and immediately wrote to Professor Brown.
Right away?
Yes, that was in 1962. I went to do research with him in 1963.
A year later?
Yes, I went in July of 1963. The book had just been published, just been sent to Japan, and just arrived at the bookstore in Sapporo. Quite a coincidence.
Suzuki-san went to the US and studied boron compound synthesis under Brown for 2 years. He was deeply influenced by Brown, not only in chemistry, but in how to be a researcher.
What was Professor Brown like? What kind of personality did he have?
He had many sides. Most people would agree that he was very tough on his students. A slave driver is what people sometimes called him. Some people would say that, but it wasn't that way for me. He never treated me harshly.
How did you apply what you'd learned from Professor Brown when you returned to Hokkaido?
Well, he told me to do work on things that will appear in textbooks someday. The way I put it is, don't rummage around in the corner of a drawer. In other words, do something new. Finding tiny problems in big, important fields where work has already been done. That's not the kind of work I believe in doing. Do something in a big, empty drawer where there is nothing at all yet. Do something totally new.
How do you know whether you're in a little corner of a drawer?
You know, working in a domain like that, all of the big questions have been answered, but there are still a few loose ends. And researchers know that if you do some research, you can tidy those up. But to do research in an empty space, a whole new domain, that is difficult. Overall, researchers know what fields are basically figured out and what is left to be filled in. It's easy to know which questions remain unanswered. That's the corner of the drawer, and the people working in that area know it. But to go into a place where nobody has gone before, that is difficult.
Discovering something entirely new in a new domain requires enormous energy. Suzuki-san overcame those obstacles. I got a sense of the drive and confidence that enabled him to do so.
It was surprising how he was drawn to Professor Brown's book by the red and black design. It seems almost like fate.
If it hadn't been for the fact that Mrs. Brown liked the colors red and black, it's possible that Suzuki-san wouldn't be where he is today.
Isn't that something?
Life is strange. After returning to Japan, Suzuki-san set out to work on the cross-coupling reaction. Meanwhile, what about his fellow Nobel Prize winner, Eiichi Negishi? Let's trace his path to this high honor.
Eiichi Negishi lives in the US state of Indiana. In 1977, he published a paper on the cross-coupling reaction that opened the door to its use by industry. Now, 75 years old, Negishi-san continues to lecture. He says that being awarded the Nobel Prize was news he had spent years hoping for.
My wife was the first one. I told her first. My dream of 50 years. Finally. I have finally fulfilled my dream. That's what I told her.
In 1958, Negishi-san started working as a research chemist at a major synthetic fiber manufacturer. But he was frustrated by his lack of fundamental research skills and an environment that demanded rapid results.
I am so grateful, of course, to my wife, Sumire. Professor Brown, my only true mentor.
Negishi-san came under the tutelage of Herbert Brown, who had also been Suzuki-san's mentor. While studying in the US, Negishi-san heard Brown lecture on cutting-edge research in organic chemistry. And at the age of 31, he became a protégé of Brown.
Unless you are involved at the top level of activity in that field, you won't know what the top level is. Based on that, I had probably been searching for someone just like Professor Brown. I realize that now.
Another of Brown's protégés, P.V. Ramachandran, worked alongside both Negishi-san and Suzuki-san under Brown. At Purdue University, Brown's favorite armchair is still kept just as it was.
This chair is Brown's thinking chair. When students used to go to his office, he would be sitting in this chair, and he would discuss our research with us. We would sit next to him in this other chair. Professors Negishi and Suzuki both sat in that chair. It has a lot of memories.
Brown had a saying that he never tired of telling his students. The department still keeps a clock inscribed with that motto.
You can read it written right here. Tall oaks grow from little acorns. I must have heard him say that, I don't know, at least 100 times.
Tall oaks grow from little acorns. It means that to achieve a big success, you must keep doing all the little things. Negishi-san still teaches at the university where he learned under Brown. 4 days after the announcement of his Nobel Prize, Negishi-san goes to share the news with his old mentor.
Professor and Mrs. Brown, 4 days ago, I finally fulfilled my dream.
Negishi-san continues to carry on Herbert Brown's legacy.
For Negishi-san and Suzuki-san, Herbert Brown was a tremendous teacher, wasn't he?
Now, Brown won the Nobel Prize himself, and so did his students. That really is astonishing.
It's amazing. And both of his students clearly embraced that motto we saw on the clock. Tall oaks grow from little acorns.
No doubt about it. Now, let's return to our look at Suzuki-san. How did he discover the cross-coupling reaction? Let's hear the behind-the-scenes story.
From LCDs to pharmaceuticals, many important products couldn't be made without the cross-coupling reaction Suzuki-san discovered. Here's how it works. LCD panels and other products are made from organic compounds containing carbon. To make a new organic compound, 2 existing organic molecules must be joined into one. But because their constituent carbon atoms repel each other strongly, the molecules will not link up on their own. Suzuki-san's innovation was to attach a boron compound to one of the organic molecules. In addition, he added a palladium catalyst to facilitate the reaction. This setup coaxes the carbon atoms to bind together, forming a new organic compound. The key to this reaction is the use of the boron compound. Using a boron compound eliminates many complex steps. With this breakthrough process, reagents need only to be mixed in a beaker.
Chemical synthesis used to be the domain of only experienced specialists. Suzuki-san transformed it into a recipe that even an inexperienced person could follow by looking at a manual and mixing up the chemicals accordingly.
In fact, before Suzuki-san made it practical, no one had imagined that poorly reactive boron compounds could be used in cross-coupling. But in his 2 years under Herbert Brown, Suzuki-san glimpsed great possibilities for boron compounds in cross-coupling chemistry.
When I went to work under Brown, there were more than 35 researchers, and most were postdocs. Only a small number were graduate students, and they came from all over the world. Everyone was saying that hydroboration reactions were interesting, but the organoboron compounds that they produced were of no use in organic synthesis. I thought the same. But then it occurred to me that their very stability could be valuable. For example, it may be used even in water-mixed solvent. Looking at how organoborons could be used turned their stability from being a negative into a big plus.
Those types of reactions must have been very difficult. Did you read a lot of papers to figure out how to make them work?
Well, of course I did. But cross-coupling was not the first work that I did. Cross-coupling was the culmination of 30 years of work that I did at Hokkaido University. It was the last 10 years that I worked on cross-coupling. Before that, I had done all sorts of things.
I did chemistry experiments at university. One thing I'd like to ask is about what happens when a reaction isn't going as you want. You can do things like raise or lower the acidity, raise or lower the temperature, or change other parameters to find the optimal conditions. What did you usually do in those cases?
Well, the easiest thing is to raise the temperature and apply pressure. That's just standard operating procedure to boost a reaction. In terms of changing the acidity, for example, you have to think about why you are doing it, and whether a higher or lower acidity would be better. You have to draw on what you know from other reactions. Everyone talks about cross-coupling, but as experts know, I worked on other reactions involving organoboron compounds. When people in general hear the Suzuki reaction, they think of cross-coupling. But that was only a fraction of my work.
Around the same time as Suzuki-san, many other Japanese scientists jumped into cross-coupling research. Here is a photograph from an international conference on cross-coupling. Suzuki-san and Negishi-san were both present, along with many other researchers in the field. Most of the attendees were Japanese. Cross-coupling as a research field flourished particularly in Japan. One such cross-coupling researcher is Tamejiro Hiyama. Among his prized possessions is a collection of the autographs of his colleagues. Of course, Suzuki-san's and Negishi-san's signatures are included. In fact, many cross-coupling reactions have been named after their Japanese discoverers, before and after Suzuki-san and Negishi-san.
The periodic table was a treasure trove in those days. Everyone just picked an element that hadn't been studied and did all kinds of organic synthesis with it. Everyone wanted to be king of the hill. Everyone was chasing new things to find reactions with new selectivity and new methods. It was like a gold rush.
What was it like in those days? Competitive?
I didn't feel much of a competitive rivalry. Fortunately, no one else was really working on coupling with organoboron compounds. I didn't really take that gold rush approach, where everyone was trying to stake a claim as quickly as possible.
Because it was an area other researchers hadn't gone into.
Well, there was that, but I'd never tell other researchers what not to work on. I was happy for others to work in that area, but few had any interest. We had already done a lot of work, and I don't know if others felt they would just be playing second fiddle to us. It would depend on the researcher, on a case-by-case basis.
So coupling, this particular research field of organic synthesis, is an area where Japan is a world leader.
Oh yes, that's certainly true. Japan is at a high level.
Overall, how do you see Japan's research outlook? What can we look forward to?
Well, in all honesty, looking at it from a global perspective, in my field of organic chemistry, Japan is right up there. There's no doubt about it.
So we should take confidence from that.
Oh, absolutely.
What about basic research?
Oh, it's very important. Applied research and basic research are not two separate things. Having good applied research requires having good basic research. As you can see from our approach, our reaction is now widely used, but initially it was the product of basic research. In order to make advances in science and technology, Japan must value basic research. I'd say that it's an absolute necessity.
Many people in the sciences watch our program. What message do you have for young researchers watching?
Well, there are so many things I would like to say. One of them is the reason that young people are less interested in science nowadays is that there is a lack of ideals and aspirations in the fields of science and technology. At least, that's my impression. And I'm not talking about ideals and aspirations that are handed down from somebody else. Now, that makes no sense. What is needed is for young people to have their own ideals, however modest, and make those the basis for their goals. Not something given to them by someone else, but something they have thought up on their own.
In my interview with Suzuki-san, whenever the subject turned to something technical, his eyes lit up and he started talking enthusiastically.
He's a very dynamic individual, and his story is a real lesson in the importance of having a passion for research and pursuing your dreams. I certainly learned a lot today.
Today, we've learned about two of the 2010 recipients of the Nobel Prize in Chemistry, Akira Suzuki and Eiichi Negishi.
Let's hope that in 2011 too there will be Nobel Prize laureates from Japan.
That's all for Science Zero.
See you next time.